Welcome to Wireless Future. My name is Eric Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you this morning?
I'm great. It's good to be back after the summer break. How are you?
Indeed. Thank you. So I think this is episode 32.
It is.
Is that correct, Emil?
Yes.
That's amazing. Power of two will happen exponentially less frequently, I think. Indeed. So today we are delighted to have a very special guest on the show, Giuseppe Caire from TU Berlin. Giuseppe is the Alexander von Humboldt Professor at TU Berlin. He's a top information theorist that I believe many in the audience know. He's a fellow of the IEEE and has won numerous awards for his work, and I think is fair to say one of the rare intellectuals in the information theory field who has contributed not only to theory but also to practice of actual systems. So hello Giuseppe, how are things in Berlin? Great to have you on the show.
Yeah, things are great in Berlin, and thank you for inviting me to this wonderful show.
All right, very good. So I guess the way we're going to run this is that, we're recording this all remotely, and Emil and I will be firing questions and stimulating discussion with you. And I thought that we could perhaps start off with a bit of retrospect, because you, Giuseppe, are a pioneer of multi-user MIMO information theory. And specifically, you're behind some of the underpinning results behind the capacity region of the MIMO, multi-user MIMO broadcast channel back, I think, even in the late 90s. And I would be curious to know, in that light, did MIMO, and especially multi-user MIMO, which is now in, I think in modern terminology, massive MIMO, did it all turn out as you thought? Or how would you describe the history here, if you could give some perspective on that?
Well, it's, I have to say, at the time where Shlomo Shammai and I started working on this multi-antenna broadcast channel, the main motivation was purely information theoretical. It was an example of a non-degraded broadcast channel, which is generally an open problem in information theory. But anyway, because of the structure, the geometric structure, the Gaussian nature of the channel, it turned out to be tractable. We got the first little result on proving some rate for two users. Then other people followed on and extended the result to a full understanding of the capacity region for this model. And this, I think, it was a very exciting result from a theoretical viewpoint. I have to say that at that time, I didn't really see how big the impact would have been in a few years to go, because the big, I think that the really turning point for this was realizing that one can acquire channel state information using TDD reciprocity. At the time, people didn't believe that this is a practical and viable thing to do. There were a lot of works claiming that reciprocal radios are too expensive, too difficult to do. One has to do calibration. And all these problems were eventually solved in very clever ways. And then, of course, with the paper by Tom Mazzetta, that basically showed that you don't need these complicated techniques that achieve the capacity. You can approach the capacity in certain conditions of when you have a lot of base station antennas and the channels are sufficiently well behaved. It turns out that linear processing is essentially good enough. And all this combined created this incredible development that now I would say multi-user MIMO is a cornerstone of the modern Wi-Fi schemes, of the modern 5G schemes, and in fact, in a certain sense, has completely shifted the attention from so-called point-to-point MIMO or space-time coding, as it was called in the 90s, in the mid-90s, a la multi and all these things geared to achieve diversity and protection against fading for the single user channel. Now we know that the wireless channel can be exploited in basically manufacturing dimensions in the space domain and blow up the capacity of wireless by orders of magnitude, which is really, I would say, an amazing development. So at the time, I have to confess, I haven't seen these all the way. It seemed a little bit science fictional and complicated, subject to perfect channel state information assumptions, and all these problems have been progressively removed to go to more and more practical design, which now we all enjoy in modern systems.
Right, where perhaps, as you suggested, the insight that multi-user MIMO systems should operate in TDD and exploit reciprocity might have been the most important one in really making full use or exploring the potential of multi-user MIMO fully. I would probably want to add also to this discussion that, to my understanding, the development of microelectronics also has progressed enormously over the last 2 decades. And as you suggested, some of these things seemed almost like science fiction, perhaps at the end of the 90s, early 2000s, but which are built today and deployed in commercial systems. And some of that is due to advances in algorithms and understanding of the actual communication theory, the insight that we should go TDD, reciprocity, rather than FDD and so forth. But some of it, I believe, is also simply owing to the progress of circuits and systems that we can build in hardware, right?
Yeah, absolutely. I remember that one of the major criticisms at the time was that calculating in real time precoding matrices to basically eliminate interference at the transmitter side in the downlink was too expensive. And now this is done for relatively large systems, a relatively large number of users. And even, we have 8 FPGAs that do this calculation in floating point. So
in real time, at almost no power consumption at all. It's just amazing, I think.
Yeah, it's absolutely.
Another point you mentioned was the, in the early days of multiple antenna systems, there was, I think, some notion that diversity would be more important than the multiplexing capabilities, and that notion underpinned, I believe, some of the development of space-time codes and space-time block codes in particular. But now with wideband systems, there isn't much of a point perhaps to seek all this diversity, not to mention with massive MIMO, where we have all the the multiplexing itself.
There has been a cultural shift, which is also probably due to the fact that systems have become more and more wideband and multi-carrier. In the old days, the fading was a foe, and this is also understandable when you have, like in a GSM, you have a 200 kilohertz bandwidth, and essentially a single carrier system, and you have a deep fade, you lose a packet, and this was the main concern. So diversity, all the emphasis on a la multi-code and space-time codes were essentially trading off spectral efficiency for robustness against fading. And now, of course, when you have a large number of subcarriers, frequency selectivity, all sorts of powerful coding techniques, including rate adaptation, this emphasis on diversity has been progressively decreased, while the emphasis on multiplexing gain. And has become much more important.
I mean, the only possible exception might be systems that are still really narrowband, right? Certain IoT, perhaps, or sensor networks, or emerging very specific systems and deployments where you just have all this bandwidth and the frequency diversity that it brings with it.
So I think here we have one of the good examples of how information theory has really been very useful. So I was in the conversation with an antenna engineer some month ago claiming that the way to designing future networks is that we look at what antennas and hardware can be built today, and we try to, as communication engineers, build something out of it. But I think this is sort of showing how you, with theory, can predict what will be possible in the future, and then wait until the point where antenna engineers can actually build the things that we were envisioning, and that this is really what leads to big long-term gains. So speaking a bit about MIMO then, what do you think is the next thing? We have talked in the podcast about distributed or cell-free MIMO. Is this the next thing to go for?
Well, who knows, right? It's certainly cell-free and distributed antenna systems is a trend, at least theoretically. Is the next thing, is like going finally beyond the cellular architecture. It has a lot of, I would say, nice features in terms of uniform quality, all these applications about low delay. Every time you have a handover in a cellular system, you have a big spike in delays, and in a cell-free architecture, it should be more like a seamless situation where a user is always at the center of its cluster. It has also a lot of problems, I would say theoretical, but also practical problems in rethinking a lot of procedures. For example, how you do initial acquisition in a cell-free system, where all initial acquisition today are based on basically are base station driven. The base station broadcasts a beacon and a user listen. If all the radio heads in a distributed say cell-free system would do the same, there would be a total cacophony of beacons. And so maybe, I don't know, going to a user-driven, user-initiated initial acquisition, who knows? Where you put the computation in a distributed fashion, you have these distributed, decentralized units, but then maybe there may be some very interesting connections with what computer science is doing in terms of software-defined network functions. Maybe every cluster processor, as every user-centric cluster processor, could be a software-defined network function that migrates across the decentralized processing units as the user moves. And so there may be very interesting connections with computer science and distributed computing. So this is certainly a direction that we know a lot on cell-free at the signal processing level. I think that at the level of the whole architecture, there is still a lot of work to do.
No, go ahead.
I would say also another direction is is going to higher and higher frequencies, because there is a clear trend, at least in the what people are expecting, that as we move say 5G, beyond 5G, 6G, people are exploring higher and higher frequency carrier frequencies and larger and larger signal bandwidths. And then at some point, things change. Like, for example, up to a certain point, the problem is not anymore sort of joint processing at the baseband level, because doing baseband processing when you have like 10 gigahertz of bandwidth, it can be very, very difficult. At the same time, propagation becomes more like a ray of light, so line of sight. But at this point, architectures like cell-free would be very useful to counter the blocking problem. You can simultaneously beamform from different radio heads and have a sort of macro diversity effect for the blocking problem, which at frequencies like sub-terahertz becomes very important. A little bit in the direction of like visible light communication, where the blocking problem is one of the major problems. So there may be some directions that are yet unexplored in this sort of distributed architectures for higher frequencies.
Yeah, these are interesting points. I mean, the fact that once you go up very high in frequency, then propagation becomes all or nothing style, like either you have line of sight or you have nothing because you're blocked. And then it seems to me that there won't be much of gains from coherent processing across the access points, and we're kind of like back to almost like a cellular system, right, where you connect to the closest, maybe best access point, and then you need a way of managing interference and mobility. But you also mentioned, I think, another thing which is very important to take home with regard to cell-free and distributed architectures, and that is that, particularly in academic work, I mean, there's lots of studies that look at how to do joint coherent signal processing and beamforming and so forth, but in practice there is a host of other problems that we have to solve. Initial access, as you mentioned, and how to send beacon signals in a way that scales also when you deploy more and more densely the access points. So certainly there seems to be a field of research which is still ripe for contributions, which is good to know. That said, I mean, the ideas of cell-free massive MIMO, I think, have been around for some time, and there are even also prototype and semi-commercial implementations. I'm thinking particularly of the P-cell concept developed by, I think, Artemis Networks, Giuseppe.
Yeah.
Could you speak to that and explain, I mean, a little bit how far is this Artemis or P-cell system from what we really think of as cell-free massive MIMO, and exactly what's going on there? What are the limitations? How well does this scale? Because scalability is a major issue, not to say the major issue, I think, in any DMIMO or cell-free architecture.
So I have been following Artemis since their infancy, when I was still in Los Angeles at the time, and I was contacted by Steve Perlman, the CEO, and Antonio Forenza, at the time was the CEO of the company. Antonio was my undergraduate student when I was in France, and then he moved to the US, and then eventually he did his PhD in Texas. So it's a very interesting company that came up with a very clever implementation. At the beginning was based on LTE, now is supporting 5G, of a distributed, let's say, multi-user MIMO system with distributed antennas. It's I would say the system is proprietary in the sense that I don't think that it is like ORAN compliant, so that their radio heads and the processing units do not fully comply with the interoperability requirement of Open RAN. It's very cleverly engineered. The radio heads are really small and cheap, and they can be attached to an Ethernet backbone. They get power over Ethernet. So I do not know all the details, all the technical details. Of course, the principles are what we all know. So it's TDD, reciprocity, with distributed calibration. They solved a lot of interesting problems, a lot of practical interesting problems, while remaining completely compatible with user devices that are of course untouched. So LTE and 5G user devices. And they have really compelling performance experiments and measures and demonstrations. I have the impression that the system is geared to cover a relatively large but localized area, like, for example, a soccer stadium, a football stadium, a shopping mall, airport hall, providing, of course, a really high spectral efficiency and very good performances for users with limited mobility, like nomadic users, or imagine like the 60,000 people attending a football match who wants to, at the same time, have camera views of the action and maybe share some pictures and do their texting or something like that. And they have examples where they have compared with respect to distributed antenna systems from legacy ISPs and the classical Wi-Fi deployment. And of course, these sort of joint processing of all of the radio heads provides a large advantage. I'm not sure that the system would scale at the level of like a urban coverage. The scalability and handling mobility is maybe not yet there. Maybe it's not even in the plans of the company, because clearly this is a small company that has eventually identified this niche market of super dense areas with very high spectral efficiency, especially with a very large number of users, because the problem there is really the number of users. At those level of density of users, even the best Wi-Fi systems collapse, and they start, being interference limited, and there are not enough channels. There are too many collisions, and we all have the experience of trying to connect in a conference hall, and when you have more than 40 people attached to a router, it becomes a problem. So yeah, so I think that it is a big step. It is a nice technology, competitive and cost effective for certain applications. I don't think that this is yet to the point of scaling to like a urban coverage with to like replace a cellular system. It would be more like a complement to a cellular system.
Yeah, it's interesting to know. I think you mentioned here two ITI works where it's really what defines the limitations, right, of cell-free or wireless in general: scalability and mobility. Mobility because of course the limited coherence during which we have to learn the channels and all that, but also because of at some point you'll need a handover from an access point to the next, or from a cluster of access points to the next, or from a access points connected to some central unit to access point connected to some other central unit, and so forth. And scalability, because at some point, I mean, you just can't grab all the data and process it at one location, right? You'll have to break up the system, and there will be natural like partitionings, and then the question is, how should these partitionings interact with one another? Worst case is that they operate autonomously, and then they will just become like big cells, and then where you are in the middle, right in between of two of them, you will be essentially what you'll have is like a multi-cell conventional system where you see interference from other parts of the system that you can't control or deal with. In a way, I think this is good news that we seem to agree that not all of these problems are solved, because it means that we still got something to do, right? So what do you say, Emil?
Yes, and Going back to this sort of going from predictions in information theory to actually building things in reality, I think you were mentioning your seminal work with Shlomo Shammai before. I think in 2001 he was writing an information theory paper about co-processing of base stations, which is sort of also predicting the gains of distributed MIMO systems. And now we are seeing how we are step by step solving different kinds of practical issues in order to implement these type of things here. And maybe the gain are bigger, but also the challenges are even larger in these situations when it comes to scalability and all of these type of things. But yeah.
So but that would be interesting to know. I mean, Giuseppe, your view on, like, if we look into the future, how far are we, or what are the real fundamental limits of what MIMO technology, be it co-located or distributed or some combination, can do for us? I mean, how large, like, antenna arrays do you think we'll ever see? We are now, I think, in commercial products for like 5G, we're at something like 100 or 128 maybe. Will we ever see arrays that are usefully built and deployed with 1,000 elements, with 10,000? With where is there like a limit where you say no? Now we hit the limit where, I mean, just make, hypothetically, think that extra additional hardware came at no additional cost. So the microelectronics could be built. Would there be like a limit imposed by physics and information theory that dictates how large arrays would ever be useful? It's like, well, if you could build an array with 1,000 antennas, then information theory would tell us that there is no point. Even if it came for free, there would be no point in building an array that's twice as large. Could you elaborate on like how you think about this? Is there a limit to when MIMO doesn't become useful any longer?
Right. This is a very interesting problem that requires, it requires a discussion at multiple levels. So basically, the philosophical point here is that at some point, models that we use will break, right? For example, if you reason at a fixed lambda, so let's say fixed carrier frequency, it means that the size of the array will grow linearly with the number of antennas, or whatever. If it is a linear array, or is a panel, like a planar array. But anyway, you increase the number of elements, the size of the array increases. And when the size of the array increases, then we have to consider the fact that most of the our channel modeling is mainly based on like a far field hypothesis, right? And at some point, this far field hypothesis doesn't hold anymore, precisely because the size of the array increases.
Well, that's certainly true. I mean that the far field assumption would break apart, but at the same time, I mean, I do agree that some channel models are based on a far field assumption, but beamforming and processing algorithms by no means need to be based on an assumption of a particular propagation model. So there is no reason for why TDD-based or reciprocity-based massive MIMO beamforming, say, should not work if you're in the near field.
Well, there will be, for example, effects like when the signal that propagates across the array, the delay of propagating across the array becomes significant with respect to the let's say, to the inverse of the bandwidth, then just the array itself becomes frequency selective, but just by that, right? So we have to reconsider certain things. It's not just that you scale the number of antennas and everything remains the same. There are the philosophical questions about the inherent degrees of freedom of the channel, for which, for example, if you keep scaling the number of antennas and if you keep scaling the number of antennas without scaling the number of users simultaneously served is a little bit of a waste. We already know from
Yes.
massive MIMO that when the number of antennas is about 10 times the number of users, somehow you reach a plateau. So you scale them at the same time. At some point, there may be some other elements that limit your degrees of freedom. For example, the rank of the channel matrix may be limited by the richness of the scattering. And then we have this philosophical question of whether the scattering is inherently discrete or is inherently continuous. Because if you have a diffuse scattering, you keep getting more and more and more degrees of freedom, right? But if you have a discrete scattering, at some point the rank of the channel becomes limited by this number of discrete scatterers, and so we enter a regime. At some point, we enter regimes that are not taken into account by the models that we somehow give for granted, and so this requires a reconsideration of the models. And once you reconsider the models, then one can come up with a reasonable and meaningful fundamental limits, because otherwise it's easy to go to misleading conclusions, right? People conclude in the past came up with all sorts of conclusions that were based on models that make sense in a certain regime, but becomes meaningless in other regimes. Well, for example, typical example was the overemphasized so-called multi-user diversity, the fact that one could schedule users at the peak of their fading and achieve enormous gains, because every now and then you have a big peak because the fading is, say, a chi-square variable. I mean, the magnitude square of the channel gain, and this has an infinite tail. And then, but okay, this is all good. All these order statistics are very elegant, but sorry, these fading models make sense when you look close to the mean. When you close to, in a large deviation sense, it doesn't make any sense, because there is no way the channel can amplify the signal. It's a passive channel. So then you get to conclusions that are mathematically correct, but on the premises of looking at the model and exploiting the model in some, in a regime that is not the regime that justifies that model. So we have to be very careful in drawing conclusions out of models without rediscussing the models. Then there is another maybe another answer here is what happens if, in contrast, instead of keeping lambda fixed, we consider smaller and smaller lambda. So we go to millimeter waves and subtera's, and then effectively the number of array elements can become extremely large without changing, the physical size of the arrays, because we go up in frequency. And then in this case, I would say it is possible, potentially possible to go to an extremely large number of radiating elements, but the antenna architecture will be different. It is probably some form of clever hybrid technology, for which you have like what is called software-defined antennas, so subarrays that already synthesize clever patterns, maybe in the RF domain directly, and then a limited number of RF chains that can be sampled, and these will seems to become now a mainstream direction, and I have no difficulty in seeing this type of development. And when we go to like terahertz and you need a large antenna gain, you may have these subarrays with really hundreds and hundreds of elements, but then the first layer of processing will be done in the RF domain, and then somehow there is a sort of projection from a very high dimensional space to a lower dimensional space, and then we can sample lower dimensional space and then do baseband processing at that level. So this is also a possibility.
Yeah, that's a fascinating point indeed, to maintain the aperture size but rather shrink the wavelength, right? I mean, I think previously when I've thought of like fundamental limits of MIMO, I have had the mindset that, well, we'll keep the carrier frequency, the wavelength fixed, and we scale up the size of the array. And then, as you suggested, I mean, beyond some point, unless we multiplex more users, then the payoff will be only logarithmical, because the only gain we get is from the array processing or the beamforming gain, right? And in turn, the number of users or terminals that we can multiplex will be related to how much coherence we have available so that we can learn their channels and so forth. But I think the problem you suggest here now, to rather fix the physical size of the aperture and see, well, how small can we make the wavelength, and how should we then correspondingly build such arrays with tinier and tinier antennas. That's a fascinating thing that, again, I think there are lots of open, interesting and relevant problems here that we're touching upon. What do you say, Emil?
Yeah, I think you're onto something important here that also struck me in the last few months, that usually when we are going up in frequency, we are thinking, oh, we will do this to get more bandwidth. But as you were saying, if you have a certain aperture size and you are squeezing in more antennas, you get more degrees of freedom because you go up in frequency. You don't need to have more bandwidth if you get more degrees of freedom, and you can do spatial multiplexing using those ones. So that might be a dimension that we haven't explored as deeply as just a simple thing of getting more bandwidth.
Yeah.
So maybe we should move on and talk about something else for a moment that is not exactly MIMO related. So, I mean, a lot of our systems today are built on OFDM, or orthogonal frequency division multiplexing. And then we have got a lot of requests to talk about this alternative method called OTFS, or orthogonal time frequency space. And then I don't know this topic that much, but since I saw that you have written a paper recently called OTFS versus OFDM in the presence of sparsity, a fair comparison, I was thinking that you would be the ideal person to ask about this. So what is OTFS? Do we get some new degrees of freedom from using this compared to OFDM, or are we just chopping up the same old degrees of freedom in a different way?
Yeah, that's a fascinating question, because OTFS is one of those things that was proposed by a startup, I think, and the way it was proposed, as usual in the startup language, is always a little bit over the top. The matter of the fact is that OTFS is just another multi-carrier modulation system. The main thing is that, there is, we are used to the time frequency plane for OFDM. We have time, we have frequency, and we can imagine the OFDM symbols as a sort of tiling of this plane with the symbols, and each symbol is a degree of freedom, let's say, in the signal space. Roughly speaking, we know that the number of degrees of freedom for a signal that spans a certain frequency, a certain bandwidth W, and lasts for a certain duration T, is the product WT. So we imagine this as a sort of grid, and the OFDM is able to fill this grid with time frequency symbols. If you do a two-dimensional Fourier transform, frequency becomes delay, the dual domain is delay, time is Doppler, and so you go to another say domain, which is the Doppler delay domain. And OTFS is essentially placing symbols in the Doppler delay domain and then converting it into the time frequency plane using this symplectic Fourier transform, which is inverse Fourier transform from Doppler to time, and direct Fourier transform from delay to frequency, and then it's modulating the thing. There are a little bit of details here and there that I will omit here, but the main point is that one can go back to the Doppler delay domain at the receiver, And then this representation of the signal becomes quite effective when the channel is essentially the superposition of a relatively small number of say multipath components, and every component is a delay and a Doppler shift. So imagine the classical two-ray model. You have two delays and two Doppler shifts, right? If the two delays are far, so the delay spread is large and the Doppler spread is large, when you see the channel transfer function in the time frequency plane is a very time and frequency selective transfer function. You see something that changes a lot in the time and frequency. So this becomes very hard to estimate in using, let's say, conventional wisdom. A conventional wisdom in OFDM is placing some pilots at the beginning or at some point in a combo of frequencies, and assume that the channel will not change across an OFDM block. In contrast, the channel is parametrically depends only on say four coefficients, two delays and two Doppler shifts, or maybe two, because you just, in fact, after time recovery and frequency recovery, you just need the difference. So it is an extremely simple channel in the Doppler delay domain, but it can be seen as a very complicated, highly time and frequency selective channel in the time frequency domain. So what we did in this paper was to consider channels of this type, so channels that are formed by a small number of multipath components, but their Doppler spread and delay spread can be large. That's why we call it in the presence of sparsity, is the so channels that are sparse in the Doppler delay domain. But then we don't use we didn't consider a conventional wisdom OFDM channel estimation, because at that point, what you can do with OFDM is to basically structure channel estimation as a compressed sensing problem. So you are trying to estimate something that is sparse in a domain, but you see a projection through the piloting scheme in another domain, and in between there is a Fourier matrix. If you do this, basically the best pilot configuration is like a random distribution of pilots in the whole time frequency plane, and then use compressed sensing to estimate the channel. And it turns out that if one does things in this way, the difference between the two systems is extremely small, in the sense that they pretty much perform the same. There is a slight gain of OTFS, in the sense that it does not use cyclic prefix at every symbol. They use only like a guard time over the blocks. But this, of course, comes at the cost of a larger processing complexity. So the cyclic prefixing of OFDM makes the processing very simple. So at the end, it's a little bit of a mixed bag. I don't think that there is a real winner. OTFS seems to be a bit better in terms of performances, a bit more spectral efficient, but requires more complexity in the detector. OFDM, when OFDM is designed to handle these, say, time-varying channels, with a correct piloting scheme and the correct channel estimation scheme, and not the naive one that performs very decently also. Of course, if one applies OFDM with the piloting scheme and the channel estimation scheme that are specified today, in the assumption of no significant channel variations across a rhesus block, in this context, it totally collapses. But this is because the piloting scheme and the channel estimation schemes make the wrong, they are mismatched to the assumptions.
Yeah, interesting. I mean, so, before I read your paper, or rather this way, when I saw your paper and saw the title, I was like, well, so where's the catch here? Because I understand that, I mean, both OFDM and OTFS are just different ways of filling the time frequency plane, right? I mean, you got T seconds and B hertz wide chunk of time frequency space, then you can squeeze in B times T degrees of freedom, and that's it. And then there might be advantages, I mean, to the OTFS in terms of if the channel is really sparse. But then I thought, like, well, however, we could do that with OFDM as well. I mean, just OFDM with the right type of signal processing would be as good, and that's basically what your paper shows.
Yeah.
Then there is this point on the loss due to the guard interval or the cyclic prefix. But to be fair, I think OFDM, you could eliminate the cyclic prefix, or you could replace it with a zero prefix. You could do various tricks there, which do come at the processing complexity, but there's nothing precludes us in principle from scrapping the cyclic prefix and applying a correspondingly more advanced equalizer at the receiver side, right? So in a way, this all comes down to processing complexity, and of course that's a relevant consideration to make.
Yes.
But there seems to be no fundamental advantage really of the specific modulation format that OTFS uses. I mean, again, you can achieve the same thing with OFDM. It's just that the signal processing will have to be adapted accordingly, and that's it. So I think the real question here is, are the channel responses really sparse in the time in the Doppler time delay Doppler domain? And to some extent, to me, that still stands to reason. I mean, it might depend on the environment we're in, and there's also this effect that the wider bandwidth you have, the more you like scatterers you and multipath components you uncover and so forth. So, is that, or do you agree with my assessment here?
Yeah, no, absolutely. I agree on the fact that relying on assumptions, strong priors on the channels is risky. At the same time, I have to say that there are techniques and conditions where one can actually force a certain level of sparsity. For example, take the case of say millimeter waves or even say the very high frequencies where something that we have seen also experimentally recently. I'm working with in a German funded 6G research hub where many other universities and research centers are involved, and so we work also with people who do measurements and experiments and have measurement equipment, antenna arrays, and things like this. And we have noticed that the effect of beamforming is not only creating antenna gain, is also basically killing the multipath. So imagine you have a two-sided beamforming, two antennas that the beams are aligned. All the multipath around is basically destroyed because they go into side lobes and they're attenuated by tens of dBs, right? Which means
I see your point. So, I mean, what you're suggesting is that if you have a large MIMO array, then the channel after application of beamforming becomes a lot more sparse, potentially in the delay Doppler domain.
If you have this type of directional propagation and have a good way of aligning the beams, these automatically will make the channel more and more frequency flat. Now, if the channel was perfectly frequency flat, we don't even need OTFS. Actually, I think that we should reconsider single carrier. Good old single carrier with one tap equalization, maybe. And,
yes, I mean, there's also the PAPR
yes,
and all
exactly.
that,
You solve
right?
the PAPR problem, and you go back to the basics with a simple time and frequency recovery, is probably good enough. Now, where OTFS may be interesting is when you do macro diversity. Imagine now you have a receiver and you have a few radio heads. Each one has a big array, and at say 150 gigahertz, they are like they are beamforming to the same receiver. Now, it's impossible to be like coherent in the sense that we do like joint processing the baseband. So you will have the superposition of, let's say, 3 copies of the same signal that come with a different phase and maybe a different Doppler shift, because the receiver is moving, and therefore if it is approaching in one direction, maybe is going away in the other direction. So you have a positive Doppler shift for one beam, a negative Doppler shift in the other beam, and then of course there will be some difference in delay just for the propagation. So at the end, you are creating a channel through macro diversity, which is inherently exactly what OTFS likes.
Well, OTFS or OFDM with appropriate processing that assumes this underlying sparsity, right?
Yes, I agree. And interestingly, this idea of macro diversity and looking at this, say, the induced channel is already quite investigated in satellites. I am aware of a project with the European Space Agency where they look at constellation of low orbit satellites, and because of the blocking problem, you would like that every receiver on the ground is in a line of sight with, let's say, 3 or 4 satellites that are moving around. So one is at the horizon, one is on the top, one is on the other side. And then if these satellites are sending the same signal, you have this macro diversity to counter blocking, but you have the problem that propagation, so they come at different delays and with different frequency shifts, and then is how to recombine them. Basically, this system create an artificial sparse channel in the Doppler delay domain, which can be very bad if it is not properly addressed, because it is time and frequency selective in a very bad way. But again, with the proper processing or the proper waveform and piloting schemes, you can do coherent combining the receiver and then get this sort of macro diversity gains.
Right. So to conclude here, man, what you're saying, and where I think I agree, is that there are specific circumstances under which we might really have an effective channel impulse response which is sparse in the delayed Doppler domain, right. And then either OTFS flat out or OFDM with appropriate channel estimation that exploits the sparsity structure and so forth could definitely, bring gains as compared to, let's say, conventional channel estimation and signal processing that makes no prior assumptions on the channels. Having said that, I still have, as a general attitude, some reservation towards signal processing schemes for communications that rely heavily on prior assumptions on the propagation channel. I'm not sure, Emil, whether you would agree with this.
I think we have a next thing to discuss that sort of have that same kind of potential issue when it comes to strong priors. On the one hand, you want to identify priors information that exist in reality, and exploit them to the as far as we can, but also don't overemphasize some things. So one thing that I think both me and Giuseppe have been working a lot on is to utilize the spatial correlation that the fading is having. So if the multipaths are not uniformly distributed in all directions, there will be some preferred channel directions that will be appearing in your statistics. And I know that you have a number of papers on the concept you call joint spatial division and multiplexing. Yeah, it's the M, which, if I explain it correctly, is like you look at the area that the base station is covering you divide it into clusters or bins, and you say that users that are in this area, in one specific areas, have roughly the same spatial channel correlation. So you shouldn't try to serve more than one of them at a time. And then you pick one person in each bin, you spatially multiplex them, and that makes sort of life much easier in terms of the signal processing. And I have a paper called Massive MIMO has unlimited capacity, where we are sort of utilizing spatial correlation to let users with sufficiently different spatial correlation use the same pilot signals, and then we can separate them anyway due to spatial correlation. And that really opens up the question, is this a too strong prior assumption that we know the spatial correlation, or is spatial correlation even something that exists in reality? Do we have stationary channels, and how large is really the region where you can say, if you move around this region, you will have the same spatial correlation? What is your view on that?
Yeah, so it's very, I mean, the whole story is very funny. I would say that, as people who do research in this field on an academic level, we need to publish. And when you run out of topics, well, then you come up with some other ideas, right? So it's funny because spatial correlation was something that at some point people start considering because, of course, the standard models are treated in, say, random matrix theory for MIMO is always IID, no spatial correlation. Then somebody says, no, actually, for such a large array, IID doesn't make any sense because you have a limited angular spread. When you do the model, you see that there is spatial correlation. And so people in random matrix theory started developing fancier and fancier theorems and that handle these complicated SINR expressions and MMC estimation error expressions with spatial correlation. There are functions of the covariance matrices of the channel vectors and so on and so forth. And then, of course, as what happens is that the next step is how we can exploit this, right? And then works like my work on JSDM or your work on unlimited capacity comes up, because there we exploit, let's say, the diversity in spatial correlation. Is not only diversity in the sense of independent channels, but also because the channels have different statistics. And the fact that channels have different statistics, I think, is I would say, almost a truism. It would be very, very strange if it was the opposite. If, in a different environments where you have a different scattering configuration, where depending on where the user are, and if they all have the same statistics, it means that the local propagation doesn't matter, only the local propagation around the base station matters. But of course, a tower mounted base station probably has not much scattering around it. Is more like what happens in the premises of the users and in the direction. So it is kind of logical that users placed in different places would have different channel statistics. Now, the problem then, how well you can exploit this and how diverse these things are. Well, if you believe in the say, ray tracing geometric models, models that are actually used by 3GPP, and they're encoded in channel simulators that everybody keep as a sort of ground truth in many standard contributions and even theoretical papers, like, for example, the channel models that you find in the famous Quadriga channel simulator. Those channels are based on a superposition of planar waves with a certain angular distribution. And if if you have disjoint angular supports, by definition, you're going to have orthogonal subspaces for these users. It's a or quasi-orthogonal subspaces, the modulo the discretization of the angle domain due to the fact that the array resolution. But for large enough antennas, you have this. Then the next question is how you know these statistics. So these statistics could be learned, could be estimated. Nobody gives them for free, although you say, okay, it's long term, but long term here means maybe on a time scale of seconds instead of milliseconds. It's still not so easy to have an accurate covariance or subspace estimation when you have let's say a couple of seconds of window on which this doesn't change, because you need a lot of samples. We are talking about very high dimensional covariances, so you need a number of samples that should be sufficient. So it's not so obvious how well this can be learned. It's also maybe a possibility now. I see more and more works that are based on using, say, machine learning techniques to learn the statistics for various purposes. So I would say, generally speaking, I think that schemes that try to take advantage of this diversity in correlation of the channels have clear advantage. Whether how well you can do it in practice is still a little bit of a question. I would also say one thing is that rely on angular sparsity may be risky. For example, if I want to do like what is called a compressed pilot, so use a short pilot dimension, because in any case I have I know that I can rely on some sort of compressed sensing technique. The channel is lower dimensional than it looks like, because there's a sort of reduced say angular diversity. It can be risky because these, especially compressed sensing techniques, collapse when the hypotheses on sparsity are not satisfied. At the same time, there are techniques now that can actually induce sparsity. For example, you can do what is called a sparsifying precoder that essentially selects only a subset of the beams. You decompose the channel in the beam space, and then you select a set of beams that is good enough to serve your users, but low enough to have effectively a sparse channel in the angular domain. So if you know that your pilot dimension is, I don't know, 10, well, you are going to select a 10-dimensional, at most 10-dimensional channel for each user by selecting the set of beams. So these are a little bit yet to be seen, not so mature, I would say, at least in terms of applications. I know that industry is extremely reluctant in doing anything that requires like a long-term estimation across the blocks. They exactly for, say, robustness or simplicity, they want everything is like block by block. You get what you get. You compute your precoder from your pilots, and that's it. Something that accumulates, remembers, keep track of the users. They say, "Oh," they're very skeptical about that. So
I think that's rather I think that's rather consistent with like my mindset. I tend to favor like agnostic designs that don't make strong prior assumptions and that really explore all the dimensions of the pilots based on assumed sparsity and so forth. Then obviously, I mean, if you do have sparsity, if you do have channel fading correlation and so forth, then you either know this magically somehow, or you can estimate it reliably, you can gain in performance. Another point I think which is worth making here is the distinction between reliance on a specific model for the purpose of algorithm design versus using realistic models in performance evaluation, right? I mean, nothing precludes us from designing our signal processing algorithms relying on independent fading, for example. But then when we evaluate performance to make predictions about where the system, how the system will perform in reality, we could certainly plug in our favorite 3D PP or whatever model there with all the correlation and all the other features, right? So the question, I guess, is where to position ourselves on this scale of like completely agnostic design, assume independent relay across all dimensions as one extreme, to systems that assume some form of correlation, to a system that maybe learns as they go along. And my preference, I think, is mainly towards agnostic systems that should work irrespective of the propagation circumstances. We could throw out anywhere and they just work. Of course, that robustness does come at a cost, and it's quite interesting to hear, Giuseppe, your comment here that folks in industry also tend to favor designs that don't rest too strongly on prior assumptions and on learning and remembering between different blocks.
I don't know if it's true in general. This is, in my experience, every time we came up and discussed these things with the industry, I noticed a certain reluctance. But
yeah, I think what I have experienced when talking to people in the industry is that they probably don't want to have like extra signaling in the system in order to just measuring these type of things. But then they might have their own proprietary implementation where they happen to know who is a line of sight user and who is a non-line of sight user because they have some tests that they are doing in their product, but they don't talk so much about it.
Yeah. So anyways, so I'm sure we're doing on time, and Giuseppe, feel like we could continue for another hour here.
I think we are reaching an hour recording now, so maybe we should have some short questions here towards the end. So looking beyond MIMO things, what do you think would be some new fundamental things in 6G that we haven't seen before? Is it things like reconfigurable intelligent surfaces, smart caching, terahertz? What do you think people should explore the most?
Ooh, that's a
short answer.
That's a very difficult question. You know what they say, it's very, very difficult to make prediction, especially about the future. So I don't know. It's certainly this. It seems to me that as we go to higher frequencies and therefore channel models become less certain, they require more characterization, more understanding. It seems that what is necessary is also a better understanding of the hardware. For example, these RIS or RIS, I never understood what is the acronym, the Intelligent Computer System or Computer Intelligence. Anyway, I call them RIS because IRS in the US is the Internal Revenue Service, which is taxes, and is somehow not so such a happy thought. But anyway, these are definitely interesting potential developments that may give like a new perspective, may solve certain problems of line of sight propagation, or maybe also manufacturing very large and steerable and large gain steerable antennas. In the old days, these things were called reflector arrays, and there is books written in the 70s on reflector arrays. Now, of course, reflector arrays would just reflect with a certain. They're not reconfigurable, But there is certainly something there that should be rediscovered. My point is that we need probably to work closer to people who design hardware and understand the hardware capabilities. For example, power consumption of A to D conversion, power consumption in power amplifiers and these components. When you go to terahertz, everything becomes quite complicated, and our usual power budget that information-theoretic, where power is transmit power, is not significant anymore. Neglecting power in the electronics and in the processing may lead to wrong conclusions. So I think that yes, certainly a higher, high frequencies and antenna design, including intelligent reflective surfaces, is a hot topic. About caching, of course, I am a strong supporter of caching. My ERC project is on coded caching, and I'm a co-author of many papers on the topic. What I frankly don't believe it will ever happen is the caching with physical layer. So there are a line of works that, including some of mine, I have to take the blame, I'm not innocent in this aspect, that somehow design physical layer in the assumption of caching. So coded caching and MIMO, coded caching and interference channels, coded caching, cache-aided interference management, all these things. Elegant stuff, difficult stuff, interesting problems. What I don't believe is that a system will ever be standardized where the physical layer is designed in the assumption of having caching somewhere. I think that if caching has a future, well, it has already a present. Caching is already used, by the way, but it's not coded caching. It's not a multi-user. It's more like the standard things that is done in the network, and maybe it's done at the individual clients, but not very interesting from our viewpoint. But I see a possible future for coded caching as an overlay technique that happens essentially above IP. Whatever happens below IP, meaning multi-access and physical layer, I don't think that this can be influenced by caching. Assuming that you can cancel interference because you have cached some files already here and there, or you design a MIMO system that assumes caching, and therefore you will get a certain expanded combined degrees of freedom of multi-user MIMO plus the caching gain. It's nice, theoretically pleasing, but I don't think that this has any future in terms of practical implementations. So nevertheless, I'm saying, for certain applications, especially on-demand video streaming, which is still one of the killer applications, the adoption of coded caching in this overlay manner, provided that one can combine IP multicasting with multicasting at the physical layer, then it becomes very interesting. And multicasting at the physical layer doesn't assume to merge caching and the physical layer in this more intimate relation. It's just that coded caching creates packets that are useful simultaneously for a number of users, and one should be able to take advantage of this. For example, you can do coded caching on top of services like eMBMS, so have like these broadcast services, but instead of sending, 10 TV channels in real time, you could handle video on demand with coded caching on top of these things. So this may actually stimulate some better multicasting techniques that at the moment are quite neglected. This could be implemented at a physical layer as a physical layer option to do multicast. Then on top of that, you can do whatever you want. In particular, if you want to do on-demand, content delivery, then you use coded caching on top of that. This may be an interesting direction, because I think multicasting has been a little bit neglected in the recent developments.
Yes. Yeah, interesting to hear your perspective on caching. I think that's a topic where I myself probably don't have much of intuition. I'm sure, Emil, whether you worked on that. But I also do agree in your last remark here that multicasting is something that's been a little bit neglected. And there's certainly topics here, even in rather pure communications theory related to 6G, that still remain open, which is good to know, of course, for all of us working in this field. So I feel like there are many other topics that that I'd like to discuss with you, Giuseppe. It might be time here perhaps to wrap up. I'm not sure if there is something final you'd like to say about, well, the past or the future, let's say in applied information theory. I mean, we did talk about 6G and some technologies that are underway there, right, with terahertz and large DMIMO arrays, caching. There's also, of course, many other things, right, like passive communication with passive energy neutral devices and semantic communications and so forth that people work on. But back to like your core subject area, information theory, there are also many important theoretical developments that have happened in the last maybe 10, 20 years. I'm thinking of finite block length information theory, for example. I mean, there's all the multi-user memory, well, already talked about, but in addition to that, there's the finite block length theory, and there seem to be other things now. Emerging grand algorithms for decoding of linear channel codes, for example. Is there something here in this context that you would like to highlight and say, hey, look, this is the future, or this is the most exciting thing that you ought to be like investing and starting to work on right now?
Well, yeah, I mean, for sure. I mean, looking back in the last, let's say, 10, 20 years, there have been a lot of amazing results that have somehow closed or almost closed long-standing open problems. And some of these results have really a lot of interest and impact on a theoretical level, maybe not so much at the, I would say, an implementation and practical level. I would say, for example, interference alignment. It's a great idea. It's a fantastic idea that somehow, in a certain sense, shows that the interference channel is intrinsically very different from other channels that we are more used to, and also explains that it's a very difficult beast to treat, right? But practically, for the Gaussian case, so for the, say, the wireless channel case, interference alignment has led to basically nothing. In contrast, interference alignment ideas have turned very powerful and have given very powerful results in other problems that are intrinsically discrete, like, for example, interference alignment in definite fields. Schemes based on interference alignment have been used for distributed, say, coding for distributed computing, coding for storage, various approaches in, say, private information retrieval, and so on and so forth. so-called gradient coding and for information theoretic secure aggregation, like in federated learning. So I would say, and it's also this explains also certain factors. Doing interference alignment in the finite fields is one thing, because finite fields are discrete, and doing interference alignment in the complex domain requires a level of channel state information accuracy that is typically not possible. And then there are other results that show that, in fact, when depending on the level of accuracy of the channel state information, you are going to lose the degrees of freedom that they are promised by interference alignment. So it was a big expectation, great theoretical advance, but in terms of practical consequences, to find a system that uses interference alignment and actually gets some advantage with respect to other more conventional techniques is very, very difficult. In contrast, there are other domains, like for example, in the domain of channel coding, going to LDPC and Taller codes, and then understanding the performance limits of finite length coding for delay limited regimes has been really like a big breakthrough. There was this sort of Folk's theorem that is very that the capacity is not attainable in practice, because there is almost all codes are good, but apart from the one that you can construct explicitly. But now we know that at least in certain important cases are very useful for applications. This is not true. We can go really close to capacity with very clever and affordable computationally feasible algorithms. So this has been really an amazing progress that has immediately reflected into implementation, because now we have LDPCs and polar codes pretty much everywhere. So I would say it's there are a lot of interesting results that with significant impact, other that for which the impact maybe is not yet so significant in practice, but may become significant, or maybe also the impact may be unexpected, like the interference alignment idea. Maybe not really useful or impactful in the interference channels as we know it, but has led to a lot of other developments in the context of more like network coding type of problems that have opened a lot of very interesting research directions. So I would say, it's a little bit difficult to to say, oh, people should work on this and that, because it's also a matter of taste, right? But certainly there are a lot of interesting topics. It's a very alive research area. And what maybe as a concluding remark, what I may say is that periodically coding and information theory have been declared mature and then dead. And periodically they have been found new topics and a new energy and new interest. So maybe now we are a little bit suffering from the fact that other domains like machine learning has become so prominent. But I think that at some point, it's like a revolving issue, and we will go back on top at some point. There will be new interests for problems that when people realize that machine learning is nice but does not solve all the problems, maybe they will be more motivated to look at the theory first.
Yes.
to say throw a neural network.
Indeed, I would agree on that.
Yeah.
Say Emil.
Yeah, no, this is a great way of ending this episode, I think, and see that there are both new problems will arise in information theory, and some of the things that have been developed over the last 10, 20 years will also make it into reality in the next decade. So, great.
Agree. So, with that, thanks a lot, Giuseppe. This has been really educational and fun, I think, to have this conversation.
Yes, me too.
Thanks again for being with us on the podcast. And thanks, Emil.
Thank you.
And see you all next time.
Okay, thank you very much.
Thank you. Bye-bye.